Well, hello everybody. Sorry I'm not there today to teach you this lesson, but here's going to be the plans for the day. If I were there, I'd answer any questions that you might have over section 3-1. I imagine you did very well on that. I've got today down into two different parts. I need to show you some more limits real fast. So I just called it a skill check. I'll do the front side of the skill check with you, so you should have that in front of you. It says Day 2 More 3-1. We'll do the front together. If you would at that time, pause the video, find a friend, and see if you guys can do the back. And then as soon as you get the back done, if you would, fire the video back up, and then let me teach you about continuity. It's going to be review for you because continuity is the same as domain. And then I got your assignment on Math Excel. So let me scroll through these next couple of pages here and kind of get to where you need to be. So if you would, look at your number 1. We hit these last time, so I don't think there'll be too much pain here. But if you look at your number 1, I would like to find the limit as x approaches 2. Now notice that there's this little dot here. That dot doesn't mean anything in this case because I'm going to try to approach an x value of 2. I'm going to approach it from the left. I'm going to approach it from the right. And as I do that, I approach a y value of 2. So my limit as I approach 2 is 2. Now look at this f of 2 though now. Remember, this says that you're given either an equation or a function. You're going to go find the y value when x equal 2. So if you look at your graph, when x equal 2, I have a y value of 1. So just make sure you can read those okay. On to your number 2, I'll pick the pace up a little bit. This says, I would like for you to find the limit as x approaches 2 from the left. So what you have to do is look at these two dots and decide which one you can approach from the left. Since there's nothing over here, I can't approach that from the left. So I'm not going to worry about that one, but I can approach this dot from the left. And as I do that, it looks like I'm approaching a y value of 4. Now I'm going to find the limit as x approaches 2 from the right. The only one I can approach from the right is this guy right here. That limit's going to be 2. Now for my part C though, find the limit as x approaches 2. This thing is not going to exist because when I approached it from the left, I had a y value of 4. When I approached it from the right, I had a y value of 2. I didn't approach the same y value, so there is no limit. Now for this f of 2, says you're given a graph. Go find the value of the y when x is 2. So I'm going to come over here to 2, and then when I come up, the solid dot happens to be at 4. So there's your number 1 and number 2. I just want to get a little more reading the graphs into you. On to number 3. The limit as x approaches 5 of this big old thing. Well, I can tell you right now, if you plug in 5, you're going to get 0 over 0, which tells us there is a limit. We just got to go get it. A lot of times it tells us there's a hole in the graph. We're going to go get the y value of that hole. So here goes our work on it. The good old f word again, factoring. I'm going to take out an x, which leaves an x squared minus 25. And then I'm going to factor that x squared minus 25 into x plus 5 and x minus 5. I'm going to factor that denominator. I know there's got to be an x there and an x there. Two numbers that multiply to be negative 15. I can make add up to be negative 2. So I'm going to go negative 5 and positive 3. Now check this out. I'm going to remove this. I just removed the 0 over 0 part, leaving me x times x plus 5 over x plus 3. And I'm going to find that limit as I approach 5. Now plug in your 5, so I'm going to get 5 times 10 over 5 plus 3. So I'm going to get 50 over 8, so I'm going to get 25/4 for this limit. So really, we've done that before, guys. There's a hole at 5 25/4. We're just not labeling it that way. We're calling it, it's more calculus style, so now we're doing limits. Okay. Now, when square roots show up, we use what we call the conjugate from your Advanced Algebra 2 days. So here's how to attack this one. I'm going to find the limit as x approaches 0 of the square root of 4 plus x minus 2 over x. Notice that if you plug in 0, you're going to get 0 over 0. There's a limit, we just got to go find it. Well, here's how we attack this. We're going to multiply through by the conjugate. So I'm going to multiply through by 4 plus x plus 2. Remember, guys, the conjugate is this expression that contains the radical with this sign changed, not that one. So I'm going to multiply through by square root of 4 plus x plus 2. Now some good things are going to happen. When I start multiplying this out, square root of 4 plus x times the square root of 4 plus x is 4 plus x. The power of the conjugate is the middle terms are going to drop out. I'm going to have 2 times the square root of 4 plus x minus 2 times the square root of 4 plus x, so those drop out. So I'm going to come over to here, so I've got minus 4. I'm going to go ahead and simplify that down here, and then I'll bring in the denominator. So I now got the limit as x approaches 0 of x over x times the square root of 4 plus x plus 2. Remember that 0 over 0? I'm going to remove it right there. So I'm left with 1 over the square root of 4 plus x plus 2. Now I'm going to plug in 0 as I run out of room. I'm going to get 1 over 4 plus 0 is 4. The square root of 4 is 2 plus 2. There's my limit, 1/4. So whenever there's a radical involved, you'll use the conjugate, which we get to do because we're just multiplying through by 1. So there's number 3 and number 4. Here comes my number 5. Notice, guys, if you plug in 0, I'm going to get 1/5 minus 1/5, which is going to be 0, over 0. Once again, telling me there is a limit. We just got to go get it. Here's how we're going to attack fractions. I would like for you to ignore this divided by x. Ignore it for just a minute. Let's focus on 1 over x plus 5 minus 1/5. Focus on that for just 1 minute. We did this back in chapter R now. Let's get a common denominator between these two. My common denominator is going to be an x plus 5. It's got to have that x plus 5 term, and it's also got to have this 5. Now when I compare this denominator to this denominator, I'm missing the 5. So 2 to 1, I'm going to multiply by a 5. When I compare this denominator to this denominator, I'm missing the x plus 5. So 2 to the negative 1, I'm going to multiply by x plus 5. Now I haven't forgot about this guy yet. So now this is going to become the limit as x approaches 0 of 5 minus x minus 5 over 5 times x plus 5. Let's go ahead and simplify that yet. 5 minus x minus 5 is going to be the opposite of x over 5 times x plus 5. Now, I'm finally going to let this divided by x come out and play. But instead of thinking of it as divided by x, I'm going to think of it as times 1 over x. So I'm going to come over here and times it by 1 over x. The reason I'd like to do that, these x's divide out. I just got rid of that 0 over 0, leaving me 1 over 5 times x plus 5. Oops, a negative 1. Now I can finally plug in 0 and get negative 1 over 5 times 5 is 25. So there's my limit. Number 6 is going to be the exact same thing. It's just written a little bit different. but we're going to write it to where it looks like that. But peek that over, hit pause on the video if you need to, because I'm going to erase this so that I have more room to write on number 6. So let me get rid of some of this so I can have more room to write there on number 6. That ought to get me about right there. So I'm going to play the same game on number 6. I'm going to think of this as the limit as x approaches 0. I'm going to think of this as 1 over x plus 2 minus 1/2 all over x. That way it looks just like number 5. This now becomes the limit as x approaches 0. I'm going to ignore this x again. At the end, I'm going to do a times of 1 over x. I'm going to get a common denominator, which is going to contain a 2 and an x plus 2. To go from this denominator to this denominator, I'm missing the 2. So I've got 1 times 2 is 2. To go from this denominator right there to this denominator, I'm missing the x plus 2. So to the negative 1, I'm going to multiply by x plus 2. So I distributed my negative 1. Notice my 2's cancel out. So I'm at the limit as x approaches 0 of the opposite of x over 2 times x plus 2. Now I'm finally going to take care of that divided by x by going times 1 over x. So I'm going to get negative 1 over 2 times x plus 2. So at this moment, I just removed 0 over 0. Now I can plug in 0, leaving me negative 1 over 2 times 2 is 4. So there's my limit as I approach 0 on number 6 there. So there's the front side of your skill check, guys. If you would, hopefully everybody's about the same point on these. Find a friend, pause the video, and then see what kind of damage you could do on the back side. And then, of course, I'm going to go ahead and start rolling over the next part. So if you need to rewind the video a little bit, more power to you. So now, hopefully the skill check went well. What I'd like to do now is have in front of you the notes for continuity. Guys, this is going to be review because we did everything here. We've done it when we did domains. Today we just call it by a different name. So instead of finding the domain of a function, today we're going to figure out where it's continuous at. Same thing. So look at your very first one there. It says state the domain of 2/3 x plus 5. Well, if you think about it, we know that's a line starting here at 5 with the slope of up to and over 3. So we know it looks something like that. The domain of this thing would be negative infinity to infinity. There's no breaks in it, and we can draw it with our pencil without ever picking it up, so it's going to be continuous everywhere. So I'm going to state that the domain is negative infinity to infinity. I'm also going to tell you that this graph is continuous from negative infinity to infinity. Domain is the same thing as continuity. Here's our second one. State the domain of the parabola x squared minus x minus 12. Well, I know it's a parabola. Open it up. It's going to be continuous when I draw it. The domain of that would be negative infinity to infinity because there's no breaks in it. There's no fractions in there. So that I'm also going to say that this graph is continuous from negative infinity to infinity. It means I can draw this graph without ever picking up my pencil, or in this case my stylus. And then, guys, now we got to tie calculus into it just a little bit. So I'm going to talk to you about the definition of continuity, and then we'll get right back into the problems. So here's the definition of continuity. It says this: let C be a number. So I'm thinking of some constant. Let C be a number within the interval a to b that we're working with, and let f be the function whose domain contains the interval a to b. The function is going to be continuous at that point C if each of the following are true. This part 1 says f of c is defined. All that means, guys, is when you're given an x value and you look up, there's a y value. There's a closed dot for a y value. So that's all part 1 is saying. F of c is defined. Now part 2 is really important. It says the limit exists. And then tie in part 3 real fast. The limit as x approaches c of x is f of c. Here's what that means. There has to be a limit in this function. And that function has to approach that value from the left and from the right. I could make number 2 happen. I could make a limit exist, but I could do this. There's a limit at x equals 2 right now. And to be truthful, let me move that over to 4. Let me move it right there. There's a limit as I approach 4 right now from both sides. But notice that I have an open dot there that's not filled in. For this to be true, this would also have to be filled in. So basically, I got to be able to draw the function without picking up my pencil. Okay. So if you would, look at your number example there. Look at the graph of f of x equal 1 over x. I'm just going to sketch a real rough graph of it. You might on your paper just do that. It doesn't have to be anything fancy. I know this is going to be a hyperbola, so I know this graph looks something like this. Early in the semester, here's the question I would ask you. State the domain, and you would look at it and say, hey, the domain looks like negative infinity to 0, along with 0 to infinity. Today, I'm just going to ask you, where's this graph continuous at? Come back here. Come back here. Just a second there, guys. Let me... Now, should be back. My PowerPoint's trying to mess with me here. So I'm going to say that this is also continuous on... Well, I'm having fits here, guys. I'm going to say that this thing is continuous. Okay, hopefully I can get it this time. I'm biting my PowerPoint. And then I'm also going to say, guys, that this is continuous from negative infinity to infinity. If you would, hopefully I'm going to roll now. Come over to your next example there. If you would, graph x squared minus x minus 12 over x minus 4. Make sure you put that numerator in parentheses. And then while you do that, I'm going to mention a couple of things. Some things that I know. My denominator is equal to 0 at 4. So right now I know something's going to happen at 4. And you already know what that is because we just tested over it. There's either going to be an asymptote or a hole. I also know that this thing is going to be continuous on the interval negative infinity to 4 and 4 to infinity. And guys, as you do that, I'm going to factor this for you. So I'm going to call this x minus 4 over x plus 3 all over x minus 4. I'm going to divide out these x minus 4s and get x plus 3. So here's something I know. I know that when you graph this in your calculator, I should see something that starts here at 3 and has a slope of 1. But I also know that there should be a hole in your graph. That hole is going to occur when x is 4. Plug into 4 and what's left like we did last chapter and get 7. So I know at the point 4, 7, there's a hole in my graph. So in this case, if we graphed it, it looks like it's continuous, but it's going to be continuous on the interval negative infinity to 4, 4 to infinity. Now here comes some new vocab for you. Now in chapter 3, instead of calling this a hole, we just call it a removable discontinuity or discontinuity. All that means, guys, is that there's a hole in the graph. I was able to remove, divide out what was making the 0 over 0 part. So come up to your next one while I'm there. I'm going to pick the pace up a little bit, get you through this. It says for each of the following, state the intervals where it's continuous, state any points of discontinuity, and then label them as removable or essential. What that means to you guys is tell me if there's going to be a hole in the graph or an asymptote in the graph. And here's how you know. Just like we did last time, I'm going to factor x squared minus 9x. I'm going to take out an x and an x minus 9 all over x. I'm going to pause for 1 second. Let's answer part A now. You cannot allow your denominator to become 0. That happens at 0. So this is going to be continuous from negative infinity to 0, along with 0 to infinity. Now it says, tell me where it's discontinuous. It's going to be discontinuous at x equals 0. I'm going to divide them out. I just removed it. So now this is going to be labeled as removable. To go a step further, I'm going to tell you that the limit is going to be, I'm going to plug into 0 in what's left. I'm going to tell you the limit is going to be negative 9. The limit as x approaches 0 is going to be negative 9. Also means there's a hole at 0, negative 9. So we answered quite a few questions there. But part A, we've done that before. That's the domain. Part B is just telling the point where there's a break. And then the difference was labeling it at, instead of a hole in an asymptote, whether it's removable or essential. Move on to your next one. I got f of x equal x minus 3 over, I'm going to go ahead and factor x squared minus 9 into x minus 3 and x plus 3. So I'm going to answer part A real fast. This thing is going to have a break at 3 and negative 3. So where it's continuous at, negative infinity to negative 3, negative 3 to 3, and 3 to infinity. My part B there, where's it discontinuous at? It's discontinuous at 3 and negative 3. Now let's figure out what they are then. Look at this one here. I can remove the x minus 3. So I'm going to say I have a removable discontinuity at x equal 3. So I could remove this guy. I circled it because it means there's a hole in the graph. I have an essential one at x equal negative 3, the part that you can't remove. I know that if you were to graph it, it's going to look like 1 over x plus 3. So to go a step further, down here where it says I got a removable at x equal 3, I also know that the limit is going to be 1/6. So I plugged in 3 into what's left. If I wanted to go a step further, I know there's a hole at 3/1/6. So tying it all up, guys, domain, we just called it continuity today, points where it's discontinuous, and then I told the world what kind they are. If I got you lost there, hang on to this one. It's almost the same. I'm going to give you f of x equal x minus 2 over x squared minus x minus 12. So I've got x minus 2 over. We're going to factor this into x minus 4 and x plus 3. So something that I know it's going to be discontinuous at x equal 4, and it's going to be discontinuous at x equal negative 3. So I know when I list the interval of continuity, negative infinity to negative 3, along with negative 3 to 4, along with 4 to infinity. I can't divide anything out. So at these 2 points where it's discontinuous, I know I have an essential discontinuity. It also means that graphically I'll have asymptotes at those points. So that's all there is, guys. Factor it, see if it divides out. If it divides out, we call it removable. If it doesn't divide out, it's essential. Removable means there's a hole. Essential means there's an asymptote. Here's a super easy one. I'm not sure why I put that such an easy one in there, but I know that this thing is discontinuous at x equal 1. I can't cancel anything out, so I know I have an essential discontinuity at x equal 1. If you're asked about the limit at that point, the limit does not exist. The reason being, as you try to approach 1, you have an asymptote. Here comes my next couple. We're getting close. We're getting close. I got f of x is x minus 1 over x plus 2 and x minus 1. So I know this thing's discontinuous at x equal negative 2 and x equal 1. For the interval of continuity, I've got negative infinity to negative 2, negative 2 to 1, 1 to infinity. Now ask yourself, will anything divide out? Notice these x minus 1s will divide out. So I have a removable discontinuity at x equal 1. It leaves me 1 over x plus 2. So that means this one is an essential, aka asymptote. To go a step further, I'm going to tell you the exact location of that hole. So I'm going to give you what the limit is. I'm going to plug 1 into what's left and get 1/3. So the limit is going to be 1/3. I've got one more, then I'm going to drop down and talk to you about piecewise graphs. That's probably been a while for you. So here goes my last one on this little section. I've got x minus 5 over x minus 5 and x plus 3, it looks like. Ask yourself real fast. I know it's going to be discontinuous at x equal 5 and x equal negative 3. Can you remove one of them? The answer is yes. I'm going to remove the x minus 5, which leaves me a 1 over x plus 3. So I know this one is removable, aka there's a hole. I'm also going to tell you the limit, plug in 5, is going to be 1/8. I can't get rid of this plus 3, so this is an essential, aka an asymptote. So hopefully we're doing pretty good there so far. If you would, drop down to the last couple down there, guys, the piecewise functions. Let me show you how to handle those, because on Math Excel today, you'll see some piecewise functions showing up. So I'm going to graph these for you. Notice that there's 3 pieces on here. I'm going to try to graph them the way you probably did in Advanced Algebra 2. You probably set up little T-charts for each of them. So I'm going to do this real fast. I'm going to set up a little XY chart for each of these. So look at that x minus 1. If x is less than 1, I'm going to pick an x value of 1. But something I know, since it just says less than, there's going to be an open dot on it. Then I'm going to pick a couple of numbers less than 1. So I might pick 0 and negative 1. When I go plug these values in, 1 minus 1 is 0. 0 minus 1 is negative 1. Negative 1 minus 1 is negative 2. So here's the first piece I'm going to graph. I'm going to go over at 1, 0, and I got an open dot. I'm going to go 0, negative 1, and I'm going to go negative 1, negative 2. So here's the first piece of that graph. There's the first piece of that graph. I should see something with the slope of 1 that's going to cross at negative 1 on the y-axis, and I do. Now let me just go pick on the next piece. I'm going to do this 0. I need to pick some points between 1 and 4. So I'm going to pick the endpoints for sure. I'm going to pick the endpoints of 1 and 4. I know my corresponding y values at those points are 0. So here's what my next little piece looks like. I've got 1, 0, which I already got an open dot there. Now I'm going to color that in. And I'm going to go to 4, 0. Closed dot there. So here's the next piece I have. Guys, it doesn't seem important, but it was an open dot and I just closed it. So far, my graph is continuous from negative infinity to 4. So far. Now let's speed up that last little piece. I'm going to do it over here. I'm going to peek on x minus 2 for x greater than 4. So I got to use 4, but I know there's going to be an open dot on it. And then a 5 and a 6. If I plug in 4, I'm going to get a 2. If I plug in 5, I'm going to get a y value of 3. If I plug in 6, I get a y value of 4. So now let me graph that piece. I got 4, 2, open dot. I got 5, 3, closed dot. And I got 6, 4, closed dot. So let me graph that little piece there. So there's where we are. Now Math Excel will ask you this question. Where is this graph discontinuous at? Well, I'm going to say that it's discontinuous at x equal 4 because there's a jump. It almost was discontinuous at 1, but we closed that in. So that's the piecewise. I'll do one more with you real fast, and then I'll have this lesson all whipped. Once again, 3 pieces. I'll try to pick the pace up. I'm going to set up a little XY chart for it. My y values are going to be 0 if x is less than 0. So in terms of my x, I got to pick 0 and some numbers less than 0. And I also know since it just says less than 0, there's going to be an open dot. And it says my corresponding y values are 0. So here's what I've got so far. I've got 0, 0 with an open dot. I've got negative 1, 0. I've got negative 2, 0. So it looks like so far I've just got the x-axis. So far this thing's continuous from negative infinity to 0. Now let's pick on this next little piece. I'm going to graph the part of x squared minus 5x, but when I set up my little chart, I've got to include 0 and I've got to include 5. I'm going to go ahead and include 1, 2, 3, and 4 also, just so I get a good graph of it. I'm going to do it right here in my head. You're more than welcome to graph it and get your corresponding y values. But when I plug in 0, I'm going to get 0. And it's going to be a closed dot. When I plug in 1, I'm going to get negative 4. When I plug in 2, I'm going to get negative 6. When I plug in 3, I'm going to get negative 6. When I plug in 4, I'm going to get 16 minus 20 is negative 4. And when I plug in 5, I'm going to get back to 0. I know I should have a parabola looking graph too. So I'm going to close in 0, 0, because that's what that says to do. I've got 1, negative 4, 2, negative 6, 3, negative 6, 4, negative 4, and 5, 0. So I know my next little piece looks something like this. I also know I had a vertex right in there somewhere. Now, since we close this in, this thing's continuous from negative infinity to 5. And my last little piece, if x is greater than 5, so I'm going to pick 5, but it looks like an open dot, 6 and 7. And it says my corresponding y values for this set is going to be 5. So I've got 5, 5. I've got 6, 5, and I've got 7, 5. So, come back here. So I've got that piece of the graph. Math Excel will ask you where it's discontinuous at. You'll look at your graph and say that this thing is discontinuous at x equal 5, because there's a jump. So guys, that's section 3-2. A lot of review, but it's different because we threw in limits, we threw in domain, range, well, no range, but we threw in continuity. So hopefully everything worked out for you. Good luck on your assignment. Bye-bye.